All right. Why don't we get started? So I've been going through the homework, and we have a couple instances, in fact, a lot of instances, about what I would consider and is considered and is academic dishonesty. So I want to take the time to discuss that, clear up any ambiguities, so that going forward in the future, we don't have these issues. And so a lot of people think, what is academic dishonesty? And, cheating, what have you, sharing answers, what have you. But that's not completely what it is. I'm fully aware of all of the very many solutions that there are out there on the internet. I'm not naive about that. I check them. And, honestly, when you just copy answers, all you're exercising is cut and paste and not really learning the material, right? If you think about anything, whether, you fly on an airplane, the pilot, he or she had to do the work, right? That's the only way you can learn to do that. And granted, I get it. People are under pressure. The homework is worth a certain percentage of the grade, but there's no substitute for doing the work. And it is painfully obvious to me when people copy solutions off the internet. For example, uh, review question 11. There's the answer, and there's all sorts of Quizlet, Corsical, Course Hero. I know what they all are, and I find this information. And so this is one of the answers. I'm not going to go over all of them, but this is one of the solutions floating out there in question. And this is a cut and paste, preserving the name, identity of the person. And this is one of the solutions that someone handed in. This is actually a solution. So I'm going to post the solution next to the actual Quizlet answer, and it's a word-for-word copy and paste, right? And so that's unnecessary. The person that did this knows who that person is. I know who that person is, and that's beside the point. The point is to do the work. And I've noticed on the homeworks there are about 4 types of answers. There's one type of answer that's a direct copy of something available on the internet. There's another type of answer that's a modification of something that's directly copied from the internet, right? It's painfully obvious to me when that happens. Then there's another type of answer where someone just gives the answer and doesn't develop the solution. And those answers, I can't really give full credit for that because I have no idea how you arrived upon the answer, right? It could certainly have been copied off the internet. And then the fourth category is someone who legitimately, honestly, honest to goodness, did the answer themselves, right? And so that last category is who I really try to give the benefit of the doubt and cater to when I grade this. I understand that you're all just learning the material. I understand that you have time pressure. I try to schedule enough time that I think everyone can answer the questions in a reasonable amount of time. There were 5 questions, and the assignment was given 7 days, right? So that's 1 question a day plus 2 days of of lag time. And so, I really, really hope people take that to heart. Whether you do or you don't, that's your own issue. Um, but certainly on homework 2, a lot more serious things are going to happen. I can't give credit to things that are copied off the internet because it's unfair to your colleagues in the class who are legitimately trying to answer the questions. There are about at least half the class where I found these kinds of issues in various degrees. And to those who are legitimately answering the questions, I thank you for that. And that honesty will certainly be rewarded. So let's not have this continue to be an issue. Homework 2 is due on the 20th. Make sure, because I do check, and this is the one warning, the consequences will get more serious going forward in the future. Hopefully this clears this up. Answer the questions yourself, right? It does you no good. It doesn't hurt me. I get paid either way, but it only hurts you. Not only in terms of the consequences, but also ultimately you're not learning the material. Okay? All right, any questions about this? Okay, so hopefully this clears this up, and I hope not to have to deal with this going forward in the future. And it takes me a heck of a lot longer to grade homework when I have to go off to 24 sources and check them against the solutions. All right. So that being said, let's exit out of here and let's just do a recap of chapter 2, which was the application layer. So where we left off, we ended, of course, homework 2 is due on the 20th, which is 2 days from now, at the usual 1 second before midnight. So we left off, we talked about TCP server, and we typed in this code in Python, and I'd hope that you're trying it yourself. Don't just passively engage the material, actively try it yourself. And I'm not going to belabor all the various steps, but there were some very important ones that I'll highlight, specifically the server socket bind. Now, that server socket bind is intended for the application to tell the operating system runtime to associate this particular process that called bind with that server port. And when we talk about, after this is done, the transport layer, we'll discuss in more detail what the purpose of that port number is. But at this juncture in the course, the port number is a unique identifier of that process to the TCP runtime. And when you think about it, data is delivered to the machine, and when it's inbound, comes to your machine off the internet, the transport layer's job is to figure out which process that data should go to. And the identifier, the binding or the association between a particular process and an identifier is that port number, right? And so for World Wide Web, HTTP Hypertext Transport Protocol, all web servers are assumed to be associated with port number 80. Now, any port number over 1024 is wide open. You can use it, but port numbers from 0 to 1024 are assumed to have particular purposes in mind, and you can Google search that and look up what those port numbers are. Okay, so that's where we left off. And of course, the server in TCP sits in a tight loop and continually accepts incoming connections. And each time this accept is called, it's a blocking call. So execution stops if there's no incoming request for connection from a client. But once this accept call returns, there's a so-called connection socket created. Now that connection socket is handed out by the server to every single incoming client request. And so the conversation between the client and the server on the server side is done through that connection socket. So when the server sends over this connection socket, it's sending data to the client, so that would be the response. When the server does a receive on this connection socket, it's getting data from this socket, i.e. from the client. That's the client request. Okay, so in a threaded application, the server then would usually hand out, do this accept, and when the accept returns, it gets back the connection socket, and it would usually create a thread to handle that particular request for the exchange with that particular client. And so a so-called multi-threaded server is one that uses a thread to handle the specific interaction with the connection socket for that server-side part of the conversation between the client and the server. Okay. Any questions about this? Does that make sense? So please do try it yourself. Granted, what we tried in class, this example, it's not threaded, but there will be an assignment for you to implement a simple web server. Okay, and so that ends the material in chapter 2. And we've done a lot of stuff or covered a lot of ground as it pertains to the application layer. We've talked about the application architectures, client server and peer-to-peer. We talked about that the application requires, bless you, certain services from the underlying transport layer. Even if you never have to deal with the internals of the transport layer, at least you're going to have to know from an API perspective, if you want to write network applications, you need to know the difference between the reliable data transport and the unreliable data transport. And that is going to dictate what version of a socket you use, whether, bless you, whether or not it's in C, C++, it's in Java, Python, or whatever implementation language you have. There are two types of sockets, one related to the reliable data transport and one related to the unreliable. And so the connection-oriented or reliable is called TCP for Transmission Control Protocol, and we'll talk about that in great detail in the next couple of slides for the next module. And the unreliable version, Unreliable Datagram Protocol, or UDP. Now you might ask yourself, why have an unreliable service? Well, the trade-off is for all of this reliability, you have a degradation in speed because some of the computational ability, some of the MIPS that you would otherwise use to send and receive data, you're using to engage in those aspects of reliability in TCP. And so the end result is for UDP, while it's unreliable, you get a lot faster raw speed when you're sending data back and forth. And there are applications where you can tolerate losses, but speed is important, things like video, things like audio, as well as other purposes. And so we talked about specific protocols. We talked about hypertext transport protocol, and that's particularly important. It's very simple, but there are a lot of other web-based APIs or API approaches that make use or piggyback on top of HTTP. Has anyone ever done RESTful SOA? Representation State Transfer, software-oriented architectures. Well, what REST does, it sits on top of HTTP, and it treats the URL suffixes, i.e. the directory structure in the GET, as if they were functions. And then it adds other pieces to the URL for the values of the parameters that it's going to call in those functions. So you can imagine exposing a function to the internet and then allowing people in a secure way to use something that looks like HTTP GET in order to call those functions remotely on a server. And it's called REST, stands for Representation State Transfer, a software-oriented, service-oriented architecture, right? And it's a method that's used by a lot of these service APIs, like the Dropbox API, the YouTube API. Whenever you write these web services, a lot of them will use REST, which is piggybacking on top of HTTP. And oftentimes when they transfer data formats, they're using JSON, JavaScript Object Notation, which is a serializable or a format that you can represent, that you can write out on disk or send across the wire. Excuse me, it's a serializable form of arbitrary objects. Okay, so HTTP is particularly important, and we talked about beyond just web, things like the header file entries, right? The header entries. And we talked about how you can use cookies and you can use if modified since to do all sorts of things related to caching as well as to maintaining state at the endpoints about a session. We talked about simple mail transfer protocol. We only talked a little bit about post office protocol and IMAP. We also talked about DNS. Now DNS is interesting because DNS traffics in something that's a layer 3 quantity, IP addresses. And the IP address we'll learn is a unique identifier that identifies the network card on your machine. Now, of course, in the early days, it was assumed that you'd only have a single network card on a machine, but most modern computers have at least two, one for wired networking and one for wireless. And so more correctly, the IP address identifies a so-called network interface, right? You have one IP per network card or network interface. And so, you know, many of your laptops, you're connected to CIS Wi-Fi, your network address will be something like 10.something.something.something. Right? So that's your IP address. And this IP address, while it's a network layer construct, here we have an application domain name service, something at the application layer, which traffics in network layer data. Now, the reason for DNS, as we studied, is to translate these names into numbers, and you need this IP address in order to create a connection, right? Whether that's TCP reliable or UDP unreliable. And then we also talked about a peer-to-peer service, specifically BitTorrent, and we emphasized the point that it's so-called self-scaling. That's going to be really, really important throughout a point in the semester. And so the self-scaling allows you for things like file transfer to get much faster speeds because every peer that joins the network not only has requests for data, but it also brings with it resources for others to use. And so by trafficking in these file chunks from multiple locations, the aggregate download speed is much, much faster. Okay. We also talked about video streaming and content delivery networks, specifically Dash protocol. We talked about different ways of encoding video, spatial coding and temporal coding, and we talked about this setup where you have all of this content scattered throughout the network, different ways you can do it. One is to push it down to the access networks, this cached content, and another is to maintain this cached content at the exchange points between global service providers. And so Netflix was the example we gave, but Akamai has made billions and billions of dollars just by offering content distribution services or caching services. And then lastly, we ended with socket programming, the API at the application layer for using TCP, the reliable service, and UDP, the unreliable service. Okay. Any questions about this? Any of this? No questions? Okay. Um, so let's continue on. We talked about all sorts of things, the message exchange. We talked about protocols in general. We talked about the role of the client, the role of the server. We talked about specifically HTTP message headers and the format of those things and what they're used for. We also talked about data, the payload that comes across. We looked at not so much about the control messages. We looked at statefulness versus statelessness. We looked at a little bit from the application layer perspective, the difference between reliable and unreliable transport. And so we're going to segue now one more level down in the hierarchy. If there are no other questions, no questions? No? All right. We're going to segue down the hierarchy with the transport layer, working our way down ultimately to the link layer. Okay, so why don't we begin? So the goals is to understand the principles behind the services made possible or afforded by the transport layer. Now, again, I said the transport layer is responsible for delivering data to the processes in the application layer. And so the transport layer header information adds this thing called a port number, and that port number is meaningful to all the other transport layers on the endpoints collectively across the network. And so this sharing essentially of the single network card, this channel of communication among one of umpteen many processes is called multiplexing, right? You're making multiple use of the same limited resource. And demultiplexing is the converse operation, the idea that you can take from this singular source, this network card, and share it among a bunch of processes. And so you need this way of uniquely identifying each process, and that's the role of the port number that we'll find. Also, transport layer, specifically TCP, Transmission Control Protocol, gives this reliable data transport. And so we'll talk about the pieces needed for reliability. It says that every piece of data that you send is successfully delivered. And that means many different things. That means that if you send byte 1 and byte 2 in that order, they're going to arrive and be delivered to the destination endpoint in that order, byte 1 and byte 2. Moreover, if these bytes get corrupted somewhere along the way, it's going to recognize that corruption and make sure that you are delivered at the communicating endpoint an uncorrupted version of it. And so that occurs by detection of corruption and also the resending of data if that data should be deemed corrupted. Moreover, when we talked about networks in general, we talked about this idea of end-to-end flow, right? And there are two things or two general categories of things that can happen when you have an end-to-end flow. One corresponds to the endpoints. And so if you're sending data at a certain rate, and let's say the endpoint to whom you're delivering or sending this data is getting more data than it can handle, right? So maybe you're running a streaming application and you're sending it video frames faster than it can display it to the person who's viewing it. Or maybe that person's pausing the video, and so they're not actively consuming video frames. And so in that case, if the sender keeps sending data at a fast rate, eventually the receiver, which has to store that data before it can be consumed, is going to run out of space. And so this idea of matching the sender rate to the speed of the consumer rate is what flow control is. And TCP, the reliable data transport, one of the things it does in order to ensure reliability is this so-called flow control, the slowing down or speeding up of the sender to match the available storage space that the receiver has. Another is called congestion control. Now, this congestion control deals with congestion at the routers along the hops along the way between the sender and the receiver endpoint. And so we said that if a packet reaches a packet switch and that packet switch can't push those packets out its outgoing link as fast as their data is coming in, it buffers them. And the more it buffers, the more they have to wait, and that's called congestion. Now, what the congestion control part is, it is also the slowing down or speeding up of the sender's send rate, but in response to congestion. And why does that work? Well, if you're getting a lot of congestion, Well, in part of the contributing factor to the congestion in those routers between the sender and receiver is the fact that you, the sender, are pushing data into the wire. And so what this congestion control says is speed up or slow down the sender in response to congestion. Because if it's congested, your packet's going to take a long time to get there, and why contribute to ultimately what will lead to packet loss. And so flow control and congestion control are two major features of reliable transport, and a lot of people confuse the two. They're both the slowing down or the speeding up of the sender, but it's in response to two different things, either the amount of storage at the receiver or the congestion status on the routers between the sender-receiver endpoint. Okay, we'll learn about the two different flavors of transport protocols, the unreliable service and the reliable service. And when we look at this, one observation we'll make is that the reliable service requires what's called call setup. And so there are two rounds of communication when you create a socket for the reliable service that uses reliable transport. The first round is to establish the resources or the connection setup or call setup. And what happens there is that the client machine contacts, or more correctly, the client socket contacts the socket on the server side, and it asks the question, do you have the resources needed to engage in this reliable transport? And these resources we'll learn include timers, it includes buffer storage space, as well as a little bit of fractional CPU in order to run the finite state machines that implement all of these procedures. Okay, any questions about this? Yes. The data is actually stored in the receiver buffer. There's a send buffer and there's a receiver buffer, and we'll talk about that in detail. But the data is stored in the sender buffer in the transport layer, and there's a paired receiver buffer in the transport layer on the receiver endpoint. And so what we'll learn is that the send buffer is used, it holds on to segments, and it'll resend. When it resends on behalf of the application, it needs to store it someplace in order to resend it. And so on the receiver side, once things arrive, they can either arrive in order or out of order. If they arrive out of order, well, it has to be delivered to the application layer above on the receiver endpoint. And so it assembles it in order in a buffer. And so there are two pieces of storage in all transport layers. There's the send buffer and there's the receiver buffer because it's two-way communication. Okay, all right. Any other questions? Does that make sense? No? All right. So let's take a look at the transport layer services. So what does a transport layer look like? Well, the transport layer, certainly it's layer 4 in this 5-layer hierarchy, and the transport layer gives the illusion to the application that there is a direct link or pipe, if you will, from one communicating endpoint to the other communicating endpoint. And so it gives this logical end-to-end transport perception to the application. Now, certainly, all you do as an application is you just take your message data and you send it into the transport layer when you do the socket send. And that's all you do. All of this resending, this error checking, this buffering, this storage, this reassembly, all of that's done by the transport layer runtime. That's done for you. You, the application, believe that you have a direct connection, and that illusion of a logical end-to-end connection is all presented and taken care of by the transport layer. So the transport layer protocols, it runs in the end systems. They don't run on the routers. The routers are purposefully kept very, very simple. Routers only implement physical, data link, and network layer. They're so-called layer 3 devices, right? Sometimes if you read the literature, you'll see the terminology layer 3 device and layer 2 device. Layer 2 device is a switch, which we'll talk about in detail when we cover the link layer. But nonetheless, the transport layer only exists at the end systems, right, on the edge of the network. And that makes sense with the general design of the internet in that all of the complexity is kept at the edges of the network, outside of the network core. Excuse me. Excuse me, outside of the switching fabric. And so what does this transport layer protocol do? You as an application, let's say you're your browser, right? You're an HTTP client. You have this HTTP GET message and you want to send it somewhere. So what do? You call socket send and you give it the text of your HTTP GET message. So then, unbeknownst to the web browser, right? This transport layer, it takes this HTTP GET message and it chops it up into pieces. And each one of these pieces, it puts in a so-called segment, right? And so as we traffic in data at each layer, this data has a different name because it has different header information associated with it. So we take an application layer message, like an HTTP GET message, we send it to the transport layer. The transport layer on the sender side, it breaks it up into pieces, right? Enough pieces so that it completely fills out the payload area of a segment. So inside of a segment, the data area is the entire message or piece of the message from the application. So it breaks up the application message into segments. It adds its header information that's meaningful to transport layers, and then it takes its segment and it passes it to the network layer, right? Okay, so once it passes it to the network layer on the receiver side, the transport layer on the receiver side gets these segments from the network layer below it, right? It gets this segment, and now it takes this segment and it can reassemble the original message if that message were broken up into pieces. So you need a way to break up messages, you need a way to identify the pieces of those messages, and you need a way to identify the application to whom it's delivered. Right, so we're going to talk about all those pieces of information that's meaningful to the transport layer. So we have more than one protocol. We have the reliable service, TCP, for transmission control protocol. It controls the transmission. And UDP, unreliable datagram protocol, which does basically nothing above and beyond what the network layer does. Okay, so the network layer implements logical communication between interfaces, not really hosts. The assumption is hosts, but technically because you can have more than one network card on a host, it's really just logical communication to a network card. And so when you stamp something with an IP address, the transport layer, and you send it down into the network layer, that network layer only tries its best to get that to whatever network card and ultimately network layer is associated with that IP address. So the network layer implements logical communication between the hosts, and the transport layer interfaces with APIs for the network layer. And the transport layer gives this logical communication, implements it between processes. And so essentially the transport layer, it enhances what the network layer can do. The network layer can't identify individual processes. The transport layer does. The network layer can't reassemble pieces of application data. The transport layer does. And so in the book, they have an analogy. And this analogy has two houses, Ann's and Bill's, and each one has 12 kids that live there. Now, in this analogy, the house would serve the role of the host, and each kid would serve the role of a process. If you want to send a letter to the first kid, well, you need to put that kid's name on that envelope, where the envelope represents the application data, that message. And so the transport protocol role is ascribed to Ann and Bill, because when the letter comes to the house, let's say a letter comes to Ann's house, Ann looks at the name and finds the first kid, whatever that kid's name is, and gives that kid the letter. Likewise, when that kid wants to mail a letter, the kid sends that letter to Ann, and the correct information is put on there by Ann, and then it makes its way out to the post office, which serves as the network layer. So the network layer is responsible for delivering to the network card. In a similar fashion, the post office, they don't care to whom that letter goes. All they care about is getting it to the house. Once it gets to the house, it's now the transport layer, Ann and Bill's responsibility to demultiplex that single location, the house address, to a particular individual for whom that letter is intended. Okay? All right, any questions about this? And the book likes to use a lot of real-world analogies. Some people find that helpful. Some people don't find that helpful. But nonetheless, it's there if you need it. Okay, no questions? All right. So what does transport layer offer? TCP offers reliable in-order delivery. And again, as I said before, congestion control, the regulation of the sender rate as a function of congestion on the routers. A flow control, which is the regulation of the sender rate in response to the amount of buffer space on the receiver. And also this connection setup, which is the establishment of the resources needed to engage in reliability. And then, of course, there's UDP, which is Unreliable Datagram Protocol. It's a no-frills extension of Internet Protocol, IP, which is at the network layer, and it tries best effort to get your datagram to the destination network interface. And so services that are not available, there are no bandwidth guarantees, and there are no delay guarantees. Certainly at some point in the future, maybe IP version 7. Right now, IP version 6 is where things are going, a lot of upgrades, but there are no delay guarantees and bandwidth guarantees. Certainly in specialized networks, you can do that with circuit switching, but not with IP switched networks. Okay. Any questions about this? All right. So let's take a look at this multiplexing and demultiplexing. In this figure, we have 3 end systems or hosts. We have the one on the left, one in the middle, and the one on your right. And we have a server, you can imagine, in the center, and then we have 2 hosts on the left and the right. And so this yellow box is a socket, right? And that's the API interface, regardless of the implementation language. It's the API that interfaces to applications, made available to applications, the services of the transport layer. And so in the diagram, what they'll typically do is they'll draw a socket that straddles the seam, if you will, that boundary between the application layer and the transport layer. And so these circles here are processes. It doesn't matter what they are. One could be a web client, one could be a web server, one could be a mail client, one could be a mail server. It doesn't matter what they are in particular. So here we have process P3 in the application layer for the host on the left. We have P4 in the application layer host on the right, and we have P1 and 2 in the application layer on the server in the center. So now you see these edges here, and these edges represent data flow direction. And so an outbound edge, right, so you have the tail of the arrow, and then there's a head of the arrow. An outbound edge represents a message send. So that could be, say, you have a web browser, you do an HTTP GET request, you send it down a socket, right? And the inbound edge, you see the arrowhead coming in, represents data that's coming inbound to that process, to the socket. And so really we have socket-to-socket communication. And with this inbound edge, that message, that segment, comes in and is delivered to a particular socket depending on a special piece of information, which is the port number. So here we have processes, we have sockets, we have the 5-layer stack, and we're not really considering at all any of the routing infrastructure in between or switch infrastructure. We're only considering, with this figure, the logical direct connections from one process to another, and that's facilitated by the sockets that connect them. Okay? All right, any questions about this? All right, so here we are multiplexing at the sender, right? So we have data from multiple sockets. Certainly more than one application can run, and more than one application can take the role as a server and therefore create a socket, right? And so you multiplex this single network card associated with the network layer, and you can handle data from multiple sockets by adding transport layer header information. And so if you're running Dropbox, Dropbox is using a socket. If you're running email, email is using a socket. Instant messaging using a socket. Video conferencing using a socket or 2, and so forth. So you have multiple sockets, each one associated with an application, and each one is sending information. So you have multiple messages coming from various applications, and they're all coming into the transport layer through their respective sockets. Okay, and so you multiplex at the transport layer by adding port information. And then on the inbound side, you're demultiplexing. And so you have all of this information, these messages, coming into the transport layer. And the transport layer examines the port number and says, aha, this is port number 80. Let me give this message to the web server. Oh, this is port number 25. Let me give this message to the email server, and so forth. Okay? All right, any questions about this? So on the inbound side of the socket, we multiplex when we come into the transport layer, and on the on the outbound side, we multiplex. On the inbound side, we demultiplex. Okay, and so the information in the transport layer header is as follows. And so we start out, we have payload data. And this payload is literally the entire message from the application layer. So when you issue an HTTP GET, inside of the transport layer segment, is the entire HTTP GET message. Now, added are other pieces of information that are meaningful to the transport layer. Really important are these two 16-bit quantities, the source port number and the so-called destination port number. Now, the source port number is that unique identifier, 16 bits, so you can have a total of 65535 or 65,535 different processes, right? If you are running more than 65,000 processes, then good luck to you, right? But nonetheless, you can have in IP version 4 65,535 different processes, and therefore a 16-bit port number to distinguish which particular process originated that message. So when you, as a web browser, issue an HTTP GET, you send your GET message in through a socket, and it is stamped with the port number associated with the process for your web browser. Now, when the web server runs, the web server assumes a fixed port number of port 80, and that's the standard for web servers. So we have the source port number describing the identity of the originator of that message. And then we also have the destination port number, which describes the identity of the process to which that message should be delivered. So if you are a client and you send message to the server, well, your client port number is the source port, and port 80 is the destination port. When the server sends back a response, those two numbers are reversed. So when the server is sending back its response, the source port number is now port 80, the server's port on its machine, and the destination port number is whatever the port number is for your client. Okay. Any questions about this? All right, so each datagram has a source IP address, and that's a network layer construct, as well as destination IP address, but it also carries a transport layer segment, which adds the source port number and the destination port number. Okay, and so remember, when we did the example for UDP sockets, when we created the datagram socket, we included a port number. And then once we did the send, we also included the IP address. The IP address says, to which machine should I send it? And the port number says, to which application should I send it? And so here we have a datagram socket instance, and we call it variable mySocket1, and it has port number 12534. And when the host on the receiver side in UDP receives this, it checks the destination port number and it demultiplexes it to the correct application, or more correctly, to the correct socket, right? So sockets are associated with port numbers. On the server side, we saw with TCP, we did an explicit bind, and I'll talk about that in a moment. Any questions about this? So certainly you can have more than one client program sending to the same server program. And in the UDP case, you can have two different source port numbers and two different source IP addresses, both sending to the same destination port and IP address, and it will still work. Okay? All right, any questions about this? All right, so let's take a look at this multiplexing and demultiplexing. And in this example, we have three machines, a server in the center. We have two host machines on the left and the right. We have process P1 in the server, P3 and P4 on the left and the right processes in the application layer, respectively. So we start out and we create a datagram socket. Remember, datagram socket is UDP. It's a connectionless service. And so we create a datagram socket. And when we do the send, it's associated with the IP address of that left-hand machine. And so the port number for that socket is 9157. And let's say we create another datagram socket on the right-hand machine, your right, and its port number is 5775. Okay, so now we create a server socket, and that's going to be a connectionless server, right? So we're going to create a datagram socket for the server, and its port number is 6428. So now we do a send, and we're going to send from the application on the left-hand machine. So process 3 does a send to process P1 running on the server. So in that particular segment, outbound from process P3 inbound to process P1, the source port number in the segment, the TCP, the transport layer header, the source port number is going to be 9157, and the destination port number is going to be 6428. So then, let's say the server at process P1, it gets that request, and it sends back a response. So when it sends back the response, it's reversed now. Because it's a response, the source port number is now 6428, and the destination port number is 9157. Okay, and of course, when that response is received by the transport layer on the left-hand machine, the left-hand host, it sees port number, destination port number 9157, and it knows that's associated with the socket attached to process P3, and so it delivers it to process P3 through its socket. Okay. Any questions about this? Does that make sense? Okay. So similar fashion, let's say that process P1 and process P4 are going to communicate. Let's take a look at the outbound edge from process P4, and I'll ask you, for P4 going to P1 outbound, what's the source port number? What's the source port number? For P4, outbound from P4 going to P1, what's the source port number? 5775. And what's the destination port number? 6428. All right, so the reverse message, let's say the server returns back a response. So outbound going from P1, inbound to P4, what's the source port number? 6428. And what's the destination port number? Okay, good. And so you'll actually see this play out in Wireshark, right? If you go back to a capture, when you're interacting with gaia.cs.umass.edu, you'll actually see when you did the get message, the source and destination port number in the transport layer was different versus when you got the response back. They were reversed. Okay? All right, so it's really, really important to understand. Okay, so that was the connectionless service, UDP. Now the connection-oriented TCP, Transmission Control Protocol, it makes use of 4 pieces of information. Absolutely, it uses the source port number and destination port number. But how you distinguish a channel of communication with TCP uniquely is by adding in the IP address. And so TCP uses this tuple, 4-tuple, these 4 pieces of information, the source IP, and the source port number, as well as the destination IP and the destination port number. And so to demultiplex any inbound segment that comes in to the transport layer on some endpoint, it needs these pieces of information to know which channel of communication this is. Okay, and so a server can have multiple TCP connections going at the same time. When you do the accept on a server socket, you're creating what's called the connection socket. And this connection socket has its own port number, and it has its own IP, and it has the IP address of the machine on which the server called accept. And so each channel of communication or socket-to-socket communication is uniquely identified by these 4 pieces of information. Okay. And we also talked about web servers can have persistent and non-persistent connections. Each non-persistent connection to load a particular object to the website represents one of these 4 tuples. Okay? All right. So this is an example of the reliable data transport, our TCP service. And here we have 3 machines. We have a server machine in the center, and we have end hosts on the left and the right, your left and your right. And so let's take a look at host on the left. It has some address A. Doesn't matter what A is. Could be 192.168.130.17. Doesn't matter, right? So we have a particular IP address for the host on the left, and application P3 is running at some port number. So let's assume that the source port number for P3 is port number 9157, and it's a client, a web browser, and is connecting to a web server that's running on the server machine in the center, and that web server, its process is associated with port number 80, right? Which web servers are. So one of the things you'll notice with these links is that there are arrowheads on both ends. It's a bidirectional connection. And when you are using TCP, you saw that the same socket that you write to is the same socket you read from. So communication is bidirectional. So here, on the outbound side, when you're sending a segment from the transport layer on the client side, you have a source IP address A, there's the A, and you have a source port number 9157. Now the destination IP address is going to be the address for machine B, which is the server in the center, and the destination port number is 80 because that's going to be our web server. Now certainly if you access a web server, you're not the only one accessing the web server, other people are. So you notice here the second host, when it wants to send a message to the web server, maybe an HTTP GET, the source IP address is the address of machine C here on the right. The source port number is 5775 from before, but the destination IP address, the targeted machine, is going to be the server machine, IP address B, and the port number is port 80, right? So what you'll notice here is you have a source IP and port, destination IP and port that uniquely identifies this channel of communication between the right-hand machine and the server. And then likewise, for the machine on the left here, it's a unique IP port, IP port for the source and destination. So every channel of communication is uniquely identified by those four pieces of information. You need them in order to have these unique channels of communication. Then you'll see on the reverse path, the server sends back a response. When the server sends back a response, you notice the source IP address is the address for that server, which is B in this case, and the source port number is 80 because that's the web server sending back its response. And then the destination IP address is the address for that client machine because it's the response coming back from the server, and the destination port number is 9157. So you'll notice how the port numbers swap, if you will, and the source IP and source and destination IP also change depending on which endpoint is originating that segment and which endpoint is receiving that segment. Okay. Any questions about this? Does that make sense? So you'll notice here there are multiple sockets. There's a socket from P2 to P6, a socket from P3 to P5, and P4 to P3, and each one of those is uniquely identified by that four tuple, the source IP, source port, destination IP, destination port. Okay, all right. Any questions? All right, so let's, already talked about all that. You can have a threaded server, and even with a threaded server, each socket that's handed out has a unique four tuple associated with it. Okay, so let's take a look at UDP. Now, UDP, you might wonder, why would anyone ever want an unreliable service to deliver segments from one transport layer to another? Well, sometimes you just want raw speed. And UDP is a no-frills extension of the network layer. And as such, it tries its best to deliver data as fast as possible, but it doesn't guarantee that it's going to get there. So if you're designing an application and you want to know, should I use TCP or UDP, you really have to analyze whether or not your application can tolerate data corruption and or data loss. And so also, data can be delivered out of order via UDP. TCP gives you the in-order reassembly as within the protocol definition. And we'll talk about that in great detail when we get to the finite state machines. And so UDP is connectionless. You just go ahead and you open up the socket and you just send. There's no establishment of resources because there's no reliability, congestion control, flow control that happens between two UDP sockets. Whereas TCP, you have connection establishment. The client machine in one round trip asks the server TCP runtime, do you have the resources needed to engage in a reliable channel of communication? Okay, any questions about this? Now, applications that use UDP go beyond just multimedia and audio streaming. DNS uses UDP. All right, so if you fire up Wireshark and you look at a DNS message, underlying DNS is UDP because DNS is a query. It's a relatively fast thing, and so the choice was to put in UDP. If you don't get a DNS response, what do? You just resend it after a few moments. Also, DNS, because it's a set of queries for resource records, it fits very compactly in one packet. And so DNS usually always uses UDP. Okay. Snmp, Simple Network Management Protocol, which we did not cover and we won't cover, is a distributed tool network application used for managing resources on a network. Now, typically, when you need to manage bits on a network, that's because there's some problem. And whenever there's a problem, you just want speed, right? You want to contact things as fast as you can. Now, UDP does not do bandwidth sharing. It tries to hog up as much bandwidth as it can, and that kind of fits for doing network maintenance and network management. You want to contact these devices right away and get them to do something. And so SNMP uses UDP. SNMP is the application layer protocol. UDP is the transport that it uses. Okay. Now, some applications try to draw a hybrid. They say, I want to have speed, so I'll use UDP, and then I'm going to implement reliability myself as an application. You can choose to do that. Some applications will do buffering as a way to try to recover or do in-order delivery, but that puts the burden on the application writer, and if something changes, now you have to tinker and tweak that infrastructure yourself. Whereas if you use TCP, as improvements happen to TCP, you benefit from that just by using TCP. But it's really up to you as the application developer. Okay, so let's take a look at the UDP segment header. Now, UDP, because it's a transport layer protocol, it has the source port number and the destination port number. So those are both 16 bits each. It also has a length field, which is 16 bits. And this length field counts the number of bytes which the UDP segment takes up, right? You need to know how big things are if you're going to send them across the wire. And then you also have a 16-bit so-called checksum, and that's a little bit of error detection, right? It's not perfect, but it works at first approximation. And if something gets corrupted, UDP doesn't resend. It just says, oh, it was corrupted. It's not getting delivered. And you don't know as a sender whether or not your message got through, right? That's just what UDP does. Okay. Any questions about this? No? So the goal for the checksum, why the checksum? Well, the checksum is a quick and dirty way of trying to detect bulk bit error changes. Now, of course, it won't detect if a single bit has changed from a 0 to a 1 or 1 to a 0, but it will detect if a large number of them have been adulterated. And so what it does is the sender treats your sequence of bits as in 16-bit chunks, and it treats them as 16-bit numbers. And it computes something that if nothing has changed beyond a certain point, that number should be intact. And what does it do? It treats your data as a set of 16-bit numbers, and then it adds those 16-bit numbers with one another. When it does that, any carry that happens from the addition, it adds it back in again, and then does a ones complement. That's called the checksum. So it takes that checksum procedure and it stuffs it into the checksum field. And then that UDP segment gets sent out across the wire. It gets to the receiver, and the receiver transport layer, it knows the first 16 bits, the source port number, the next 16 bits is destination, the next 16 bits is a length, so it knows how many bits it has, and then that other 16 bit in the header is a checksum. So it takes that checksum that came across the wire, and then it recalculates the checksum of that segment that just received. Now, if the calculated checksum and the one that was sent are the same, then it assumes that there is no error. If the calculated checksum is different from what was sent, then it assumes, there's some error, so I'm not going to deliver this. I'm going to consider it as being corrupted. Does that make sense? Any questions about this? All right, so let's go ahead and go through an example, excuse me, of computing the checksum. Now, this assumes just two 16-bit quantities, as you can see. We're going to add the first 16-bit number to the second 16-bit number. And if you're dealing with binary arithmetic or base 2 arithmetic, there are three different scenarios you can have when you're adding a digit or adding two digits in base 2. So the first one is you have a 0 and a 0. Well, if you add those in base 2, that's a 0. Okay. If you have a 0 and a 1, or a 1 and a 0, you add them, right? That's a 1. That's a 1. Okay. Well, if you have a 1 and a 1, well, what is that? That's a 0, but you carry out a 1. And the reason for that is, recall, this is 2 to the 0, which is 1, and that's 2. Next column is 2 to the 1, which is 2. If you add 1 and 1, that's 2, right? But in base 2, a 1 and a 1, you write 0, carry out a 1 because it's going to end up as being 1, 0, which is 2. Does that make sense? So the next thing that can happen, you'll notice here, I can carry out a 1. If I add something, I can also carry in a 1 or carry in a 0. If I carry in a 0, it's a moot point, right? If I carry in a 1, well, let's call this column, this row, I carry in a 0. So I could also have a 1, 1 where I carried in a 1. I could have a 0, 0 where I carried in a 1. I could have a 0, 1 or 1, 0 where I carry in a 1, right? So it's a digit from before, from the previous column, preceding column where I had carried in a 1. So if I carry in a 1 in this 1 plus 0 case, well, 1 plus 0 is 1. Carry in a 1, well, that makes it a 0, carry out a 1. Does that make sense? So if I have a 0 plus 1, carry in a 1, well, that's 0 plus 1 is 1. Add that 1 that I carried, that's a 0, carry out a 1. Okay? If I have a 0 plus a 0, 0 plus 0 is 0, but I add the carry in of 1, that's now a 1. And if I have a 1 plus 1, right, that's a 0, carry out a 1, but a 0 plus a 1 is a 1. Does that make sense? Okay, so let's take that into consideration, and let's look at this example here. And I'm just going to sit at the desk here, and I'm going to put the cursor over the columns to make it a little bit easier to see. So when I add two 16-bit numbers, I'm going to go from least significant bit on the right to most significant bit. So I have a 0. I just lost my cursor. There we go. I have a 0 and a 1. There's no carry, so that's just a 1. Next column, I have a 1 and a 0. That's just a 1, okay? No carry. I have a 1 and a 1, right? No carry in. 1 and a 1 is 0, carry a 1. So now I'm carrying a 1 to this fourth column. 0 plus 0 is 0, but I'm carrying in a 1. That's this case here. So that's now a 1. I don't carry out anything, okay? So the next column, 0 and 1 is 1. 1 and 0 is a 1. 1 and 1 is a 0, carry out a 1. So I carry in a 1 to the next column. 0 and 0 is 0, but I add the carry in of 1, and I have a 1 down here, okay? So there's no carry out, so that's 0 and 1, that's 1. 1 and 0 is 1. 1 and 1 is 0, carry out a 1. So in this next column, I carry in a 1. 0 and 0 is 0, plus the carried in 1 is 1. 1 and 0 is, 0 and 1 is 1. 1 and 0 is 1. 1 and 1 is 0, carry out a 1. So I'm going to carry in a 1 to that last column. 1 and 1 is a 0, carry out a 1, but I add the carry in of 1. So that's a 1, carry out of 1. Now, if you have a carry out of 1 out of the most significant bit, you take that carry out and you add it back in to the beginning again, right? That's just the scheme for this checksum if you have a carry out, the most significant bit. So if we have a carry out, what do we do? Well, this is our result, and then we're going to add in that carry out of 1. We're going to wrap it back around. So if I carry in a 1 to this digit, 1 plus 1 is 0, carry out a 1, right? So I have 1 and 1, that's another 0, carry out a 1. All right, that's a 0, plus the 1 that I carried is a 1, and everything else remains the same. Does that make sense? Okay, so that's the addition of the two 16-bit integers, and what the checksum is doing is treating every 16 bits as an integer, and it's adding them together, right? So you're going to get all this craziness with carries out and carries in and all that stuff. So once you're done, the resulting sum is this row marked sum. And to make it a checksum, you take this sum, right, which wraps back around the carry out from the most significant bit, and you compute the ones complement, right? So ones complement is everywhere you see a 0, you change it to a 1. Everywhere you see a 1, you change it to a 0. So here I have 1, 1, 0, 0, 0, 0, 1, and so forth, right? And that result is my checksum, and that's the 16-bit number that you put in the checksum field of the UDP segment header. Does that make sense? Now, this is good for catching bulk uh, data corruption, right? And typically what happens when you have interference that changes 1 bits to 0 bits or 0 bits to 1 bits, it's not just a single bit that typically changes. It's usually a block of bits, and this will catch blocks of bits of a certain length. Okay. Any questions about this? Does that make sense? Okay. So let's take a look, and we'll end in this section to see how far we get at principles of reliable data transfer. And this is going to be the model we use when we talk about the behavior of TCP, right? And in the book, they use finite state machines to do that because literally you could implement this. I wish we had an advanced undergrad course in networking because looking at the Linux TCP runtime implementation is pretty interesting, but it's much more complex than the finite state machine that we look at in this class. But nonetheless, it gives you enough to try to start to make sense of it. But nonetheless, reliable data transport. So in this figure, and this is in the book, we have the application layer above. So we're representing the seam between the application layer and the transport layer. So we have the application layer above. And what the application layer sees, or at least from its perspective in terms of the services it gets from the transport layer, is it thinks it has a reliable channel between the sender endpoint and the receiver endpoint, right? That's what the application layer thinks it has. Now the transport layer, when we look at the seam between the transport layer and the network layer, the transport layer, when it gives data to the network layer, to the transport layer, the network layer is unreliable. And so the application thinks it gets reliability when it sends into the transport layer, but the transport layer knows it's unreliable when it sends to the network layer below it. So everything that we study for the transport layer is this implementation of reliable data transport, RDT. And in the book, they developed this RDT, reliable data transport, in stages. And these stages make various simplifying assumptions, and it slowly relaxes those simplifying assumptions. And so what this RDT consists of is, we'll see here, an RDT send, right? This RDT send is that interface that the application layer uses with the transport layer in order to do a reliable send. So it says reliable data transport send. Okay, and then all this craziness goes on inside of the transport layer, which is the implementation of the protocol for reliable transport, right? And we'll peel this back in stages and talk about all the features, how you get this connection set up, you get the congestion control, you get the flow control, all of these things, as well as so-called pipelined send. Okay, so RDT send. This is called by the application layer above. Now, of course, you say socket send. This is just purely conceptual, but it captures every single aspect of the TCP runtime. And when I say runtime, I mean the implementation of the protocol as it runs, the stuff that it does whenever you call send or receive. And so the application layer from above, it calls RDT send, and it passes as payload or as a parameter to RDT send the application layer message. And so if you're dealing with a web browser, it's that formatted HTTP GET message and all that good stuff, and it sends it as payload data or a parameter to the RDT send. Now, the transport layer, it calls UDT send, unreliable data transport send. That's the service that the transport layer gets from the network layer. So it's given the illusion to the application above that it's reliable, but at the end of the day, it's not reliable. And it's making use of this unreliable data transport send in the network layer in order to implement reliability. Okay? So the UDT send gets called by the transport layer. Now, of course, if something's unreliable, you might send and it doesn't get there. So what do? You send it again. And if it doesn't get there, you send it again and send it again. And eventually, one of those times is going to eventually get through. Now, of course, if the network is highly unreliable, the end-to-end flow rate is going to be very slow, right? Because a smaller percentage of the time, your segments are making their way through. But if your network is fairly reliable, well, you're going to get very good end-to-end throughput because more percentage of the time, your data is going to make its way through. But nonetheless, the transport layer on the sender side calls UDT send, right? And it's used to try to transfer this segment across the wire. And those are the services that the transport layer makes use of from the network layer. Okay, so we have this unreliable channel. It doesn't matter what it is. It could be wireless. It could be wired, what have you. And we get this RDT receive. That's called when the packet arrives on the receiver side. Now, of course, an interrupt is how this works. The network card gets this data, an interrupt is thrown, and then that buffer full of information is delivered in through the device driver, through the link layer, and makes its way up to the network layer, which delivers it to the transport layer. Now, this RDT receive is what is called when a packet arrives on the receiver side of a channel from the perspective of the transport layer. That's really important to remember. So we have this unreliable channel that eventually, if you keep resending enough times, eventually it'll make its way through, and RDT receive is called when it arrives at the receiver's transport layer. Okay? So now it's at the receiver's transport layer, and the receiver's transport layer calls deliver data, and that's what's used to send this data to the correct application above. Now, certainly, if this channel is reliable, if you send the first segment, the second segment, and the third segment, maybe the first one gets through, the second one gets lost, and the third one gets through. So all of a sudden, you have some missing gap of data. So what happens? Well, if you have a missing gap, you're going to have to store something here. All right, so there's buffer space at these endpoints used to store packet information because some of those packets might not get there. You have a gap. And once it gets there, let's say packet 2 is reset, and all of a sudden now you have segment 1, segment 2, segment 3 in storage. Once you have a contiguous block, then you deliver that data to the application above. And so one of the things you need inside of this transport layer protocol implementation, this reliable data transport, is you need the ability to store segments, plural, more than one segment worth of data. And the reason why you need to store more than one segment worth of data is because this application message, remember, one of the things the transport layer does is it takes this message and it chops it up into pieces. Now, of course, a packet has a fixed size. Now, in IP version 4, 4096 for regular landline is the standard packet size. Can you adjust it? Absolutely. Now, let's say you have a high-def video frame, and that high-def video frame will not fit in that 4096 bytes. So what does it do? Well, your application says take the video frame, send it. Well, the transport layer RDT send merely accepts this huge piece of data. Underneath the covers, this transport layer stores it, and you need to store it on the sender side as well. So you need buffer space. It stores it, it chops it up, it takes the first piece, puts it in a segment, adds header information, does the unreliable send. Takes the next piece, puts it in a segment, adds header information, sends it in an unreliable channel. So this happens many, many, many times, and it can happen, you can have several pieces of that message straddling more than one segment sent out across the network. So not only do you need buffer space on the receiver side to construct that message, right, and ultimately deliver it to the application layer above, you also need buffer space on the sender side. Because what happens if you send the second piece and it gets lost? Well, the sender is waiting to hear back. Did it get there yet? Did it get there yet? If it hasn't heard back in a long time, it assumes it was lost. Now it needs to resend. Now remember, to the application, it doesn't know, it shouldn't have to know, and it shouldn't care if a piece got lost. That's the transport layer's responsibility. So in order to resend things on behalf of the application that gave it the data, it needs to now store it so that it can guarantee it can resend it, because you can't resend what you don't have, right? So you need the ability to time things, you need the ability to store things, and we'll talk about those resources in great detail and how they interact with one another to give the illusion to the application layer above that reliable delivery is happening. Okay? All right. Any questions about this? Okay, let me do a time check. 109. So in the description in the book of how the protocol works, they use a finite state machine. And this finite state machine is a graph where each of the nodes in the graph represents a state or condition that's happening in this TCP runtime. And it has a bunch of edges, and these edges are so-called decorated in the following fashion. And so they're decorated with this construct, and on the top of this horizontal bar, we have the name of the event that causes a transition. And so each edge is labeled or decorated with an event that occurs that triggers a transition to a different state. And then underneath this horizontal bar is the action that's taken when you get this state transition. So you start out in some waiting state, an event occurs, causes an action to happen, and now you transition to a new state. That's the do something when this occurs, and it's literally a finite state machine implementation. Okay? And so in the book, they incrementally develop the sender and the receiver side. And when I say sender and receiver, I mean the sender's transport layer and the receiver's transport layer, precisely this diagram from before. All of that's happening as a conversation between the sender's RDT implementation and the receiver's RDT implementation. So all of this activity is happening in the transport layer on the sender and receiver side. Does that make sense? Okay, any questions about this? No. All right, so we'll end with this. This is RDT 1.0. And RDT 1.0 is very simple, and it makes the assumption that the network layer is completely reliable, right? It's a naive, very simplifying assumption. But what they do in the book is they start with a naive assumption, and then they add more and more realism. They say, what if it's perfect? Okay, what happens to the behavior on the sender side and the receiver side? Then they say, okay, what if messages can get corrupted, right? What happens to the sender side and the receiver side? Okay, what if messages can now be lost? What happens on the sender side? What happens with the receiver side? And so they increasingly add more and more complexity to this network layer, this unreliable data transport, and incrementally develop the machinery for what happens in the sender and receiver transport layer endpoints as a result. Does that make sense? Okay, so here we have a different finite state machine, which describes the behavior for the sender and the behavior of the receiver. So we start out in the start state, and that state's called wait for a call from above. Now that call from above is a trigger that happens when you call socket send, right? So you call socket send. RDT send is called from the application layer, calling into the transport layer through the socket, and it gives it as a parameter that data. That's your HTTP GET message, and you say socket send, you give it a buffer full of that message data from the application. So what does the sender do? It makes a packet of it. When it makes a packet, it wraps that data in a transport layer segment, and then it does the UDT send. It sends that transport layer segment over the network layer, this unreliable data transport. Does that make sense? So this happens again and again and again. So it waits for the next call, does the RDT send, wraps it in a packet, and does UDT send. Waits for the next call, waits for the next call, does it again and again and again. Likewise, on the receiver side, the RDT receive is called, and that's when that segment is delivered to the receiver side transport layer over the network layer below. So RDT receive is called, and that's where it comes from below, right? That's the RDT receive. So it arrives in the receiver transport layer. And what does it do when it gets that RDT receive? Well, first it's waiting for the call from below. The RDT receive happens on our transition. The action taken, it extracts the packet from that, extracts data from that incoming packet, and then delivers that data to the correct application above. And that happens again and again and again. So the sender is triggered on the RDT send from above. The receiver is triggered from the RDT receive from below. And if we go back 2 slides here, the RDT send triggers the behavior of the sender side. The RDT receive triggers the behavior of the receiver side. Now you'll notice here, and I'll end with this, This is a unidirectional communication from the sender to receiver. The same thing happens in the opposite direction. You just reverse the role of the sender and the receiver. You'd have this state machine repeated here and this state machine repeated here. And so it's bidirectional communication, but when we talk about the behavior, we only talk about it from the perspective of one direction. Okay? All right, any questions about this? Okay, so we'll end there. It's now 1:14. I will see you all on Thursday.